So good afternoon, my dear students. So I am going to discuss about the control rectifier and DC converter for DC drives for our traction applications. Okay, in my last class I discussed about different traction motor activities for DC motor drives. Then discussed about the advantages. Okay, what are the different types of control? Okay, what are the different types of power electronics control for the single phase DC drives? Okay, so for the single phase and three phase DC converter drives. Okay, for the traction motors. So right now I'm going to discuss about the different chopper circuit. Okay, basically I am telling about the control rectifier. Okay, so control rectifier means you know that overhead connections are in DC AC. Okay, in Indian convention you know that it is 25 kV AC is there. Okay, so overhead connections are AC. So if you try to fade the traction motor, normally we are considering it's a DC motor. So what we need to do, we need to convert that AC. We need to convert that AC in form of DC. Okay, means control DC. So then after that we can able to fade that. After that we can able to fade the DC to the armature of the motor. Okay, so here you can see the AC supply is there. Okay, after that AC DC control rectifier. Okay. Control rectifier. So what is it known that AC DC control rectifier? Then we will give it the VA, means your armature voltage is there. Okay, so in the armature voltage is there, so it is your armature current, and armature current is passing through the motor. Okay, motor armature, and finally we will get that value. Sorry, finally we can control the value of VA by changing the firing pulse of the control rectifier. Okay, then field excitation is there. Okay, field excitation means it is separately excited. Okay, if it is separately excited motor, then what happens? So we will give that AC supply to again control DC. Okay, AC to DC, that is diode bridge or the control rectifier. So we can change the field also. So we can possibly it is happen for the field control. Okay, so control rectifier fed drives. Then here you can also use the chopper fed drives. In case of chopper means that DC may be controlled. Okay, here the DC is control only changing the firing pulse. If we want to control the DC, so what we need to do? So we can directly use one diode rectifier. Okay, so AC supply we just convert all the AC to the DC portion. Okay, then the DC power or the DC power should be controlled by using the DC converter. So by mistakenly it is written AC, so actually it is it should be DC. Okay, so it should be DC, that one. Okay, so it is not AC, it will be DC. Okay, so DC converter, it should be the DC line. So DC converter. So by using DC converter, so we can, so by using DC converter we can control the input voltage, control the armature voltage of that motor. Okay, so of that motor, and finally we can also, another circuit is there for the AC supply for the AC DC rectifier. Okay, in that case you can use the diode rectifier or the control rectifier. Normally we are using diode rectifier. Okay, then we can also control the voltage of your field. Finally that field current is there. Okay, finally we will see the chopper fed DC drives. Here you know the basic structure of the shunt motor. So we are using the shunt motor means that it is your armature coils. Okay, armature coil and armature coil resistance and is your armature. Okay, so here you can see that motor load torque is so here you can see that motor load torque is motor load torque is countering your load torque. Okay, so motor torque means TD is your main torque, is countering your TL. Okay, so it is your J means it is a moment of V is a moment of inertia, so J is your inertia. So you know that motor speed can be varied by using controlling the armature voltage VA, known as the voltage mode control, controlling the field current IF, it is known as also the field control, and the torque demand which corresponds to the armature current IF or the fixed field current IF. Okay, the speed which correspond to the rated armature voltage or the rated field current and the rated armature current is known as the rated base speed. Okay, so here you know that expression of the speed. Okay, so what is your, you know that VA equal to what? EA plus IARA for case of motor. Okay, so what is that value? So VA minus IARA equal to E equal to what? E equal to generated EMF equal to Zn phi b by 60A. So Zn, okay, phi is not constant. You can say make it constant. Zn phi. P is also constant by 60A. So you can make it omega means it is your you know that is that value. So directly it is coming that expressions from the omega from the induced EMF. Okay, so from the induced EMF you will get that one. So that value. So directly you can replace that omega, then you can find out the value of omega. Okay, so if you vary any of them, means if you vary the armature voltage, so speed will vary. If you vary the armature resistance by adding with additional rheostat with there, so then again it will vary. So you will also get the varying the IF. IF means phi. Okay, K phi n na. So Eg equal to K phi. Okay. So K phi omega n, Z in phi by 60n. So 60n means 1 by n means again it is function of omega, no? So that is coming directly. So flux also been controlled. Okay. So by this way you can vary that value. Okay. So here you know the speed torque characteristics. So you can understand that value. So this is up to your base speed. In base speed, what you need to do? Constant torque. Okay. And after that, constant power. Okay, so for constant torque, what you need to do, you can vary the armature voltage and armature resistance. So after that portions, you can make it constant the torque. Then what happens? Why the power is constant? Basically, you have to vary the field. Okay, if you have to vary the field, definitely that torque will be changed. Okay, so after that value, the torque will be changed, and it is varying like that. You know that the expression of the torque. Okay, so that is directly function of phi. Okay, so field control means you are controlling the phi. So phi has been changed means so torque also been changed. Okay, so it has been changed there, and finally you can get that speed. Okay, so speed and it is your torque. Okay, both you are getting. So it is your armature current IA. IA is your armature current, and you will get that line of that armature current and field. Initially that field current is fixed. Okay, for the constant torque operation, as torque is a function of phi. So phi is fixed means torque also been fixed. Okay, so after that what happened? Phi is varying. Okay, so phi is varying. So torque also been varying, but how it will be vary? It express. You know the expression of the torque equal to sometimes what happen K phi IA. Okay, so phi is varying, but sometimes what happen in DC series motor I also function of it IA K phi IA. Okay, so that IA is series sometimes in DC series motor it is a function of a phi. Why? Basically flux line means field winding and armature winding both are in series. Okay, so in that case I is directly proportional to phi. So torque is directly proportional to IA square or phi square or phi square. Okay, so it will be rectangular way it will be varying. Okay, such that is written over here. In practice, for the speed less than the base speed, the armature current and the field current are maintain the constant. So why it is constant? That I am telling you. The flux line is more or less constant to meet the torque demand. Okay. And the armature voltage VA is varied to the control the speed. Okay, for the speed higher than the base speed, the armature voltage is maintained at the rated value. Okay, and field current is varied to the control the speed. Okay, however the power developed by the motor, equal to torque into speed, that is remain constant. Figure below shows the characteristics of the torque, power, armature current and the field current against the speed. Okay, that you can understand. So it is your field current IF. Okay, and here you know that power is more or less fixed. Power P equal to T into omega. Okay, torque and omega it varies proportion such that way. So power should be maintained fixed. So it is basic characteristics. You can understand what you need to do. So, oh sorry, what you need to do. So you know that expressions that IA equal to IF. Okay, IA equal to IF for series motor, IA array and it is IF array. So both of the cases you can see that in series motor the field winding and armature winding, both of the winding having more cross sectional area for getting more current. Okay, for avoiding the loss. Okay, so what will be the speed control equations? Omega equal to VA minus IEA within bracket IEA, sorry, RA plus RF, bracket close and multiplied with the highway. So it is your KV and IF. Okay, so it is your torque expressions. IA is there. Okay, so it is your constant torque and constant power. Okay, so torque making constant, then torque line is varying. So similarly, IA is there, IA line is fixed, then it will be varying to IA. So power line, you know that initially constant, it is more linearly changing. Okay, linearly changing, then it is make it fixed. Okay. So what is we can observe from this study? So controlling the armature voltage VA known as the voltage control, and armature current IA will measure the torque demand. Okay, the series motor can provide high torque, especially for the starting. For this reason, the series motor is commonly used for the traction application. So friction, it can overcome the static friction well manner. Okay. So basic characteristics, if you see another point, so you can understand. So for the speed up of the base speed, okay, for the speed up of the base speed, so armature voltage is vary and the torque maintain the constant. So rated armature voltage is applied. The speed torque relationship for follow the natural characteristics of the motor and the power, that is torque into speed, that should be remain constant. Okay. As the torque demand is reduced, the speed definitely it will be increased. Torque demand is reduced means speed is increased. Okay. Why? Basically for maintaining the T omega, na? Maintaining the power fixed. Okay. So you know that maintaining the power fixed. Up to that value, then power will be fixed. Okay. But here torque and I means if you make it change, okay, so if you make it change, so definitely power also mean make it fixed, okay, means but linearly varying, but considering all those 2 points. Okay, at the very light load the speed could be very high and is not advisable to run the DC motor without load. So these are the very basic points. Okay, so now we have to think about in motoring operations and different mode of operations. Okay, so first mode of operations is your motoring operation, T omega. So if you draw the x-axis, if you draw the axis, okay, or if you give the name of the axes, so one axis will be T axis, another omega. So both of the cases T and omega both are in positive, so you can say like that it is in positive, power is positive. Okay, so it is motoring operation. If one of them is negative, okay, if one of them is negative, so you can say like that it is second mode of operations, but power is negative. In third quadrant, what happened? Both are negative, torque, omega, both are negative. Okay, so but their product means power is positive. Okay, so that's why it is known as reverse motoring. Okay, okay, so that is known as reverse braking. Okay, that is known as reverse braking. Reverse braking and motoring both are same. Okay, then next quadrant again power is negative, so it is called plugging or the reverse motoring. Okay, so in case of reverse motoring, any of them are negative, so motor will be rotating in reverse direction. That's why it is called reverse motoring. And normally second quadrant, what happens? The first braking you can observe. Okay, but in third quadrant both are negative. Na torque and omega both are in negative direction. So negative means normally your positive direction means you are considering it is anti-clockwise. Normal convention is anti-clockwise is your positive direction. So that is your reference. So any of them are reverse, then your standard consideration. So you can say like that it is negative. Such that way. Okay, so that's the way to understand. Okay, so I think you are able to understand. Then what is reverse motoring in plugging? What happened? The rotations of the thing again any of them are negative, so rotation of the motor is reverse direction. So that is called reverse motoring. And in third quadrant, why it is called reverse braking. So normally what happens in braking, any of them are negative. Okay, so in braking any of them are negative, so it is coming torque or omega. So okay, both of them are any of them are negative, so power is all the time negative. But in reverse braking the power is positive, so it is also similar to your motoring operation. That's why it is known as reverse braking in the third quadrant of operations. Okay, torque and omega both are negative. That is the basic reason. Okay, so I think all of you are able to understand. So second quadrant operation, it is known as regenerative braking. It having some specific name. So dynamic braking also be there. That is your third quadrant operations. Okay, as well as the plugging. Plugging is your fourth quadrant operation, and among all them you can accommodate in the fourth quadrant operation. So both are observable in the fourth quadrant operations of drives. Okay. So basic circuit diagram is given. So it is very basic. So first year level knowledge. This is for it. So that's why I am not going to discuss on it. So it is your series motor configuration, circuit configuration, separately excited motor. Okay. So then regenerative braking, what happened? In regenerative braking, you can say like that the arrangement of the regenerative braking is shown in the figure. Okay, so it is for regenerative braking. So previous picture it was for motoring operation. Now you can see the regenerative braking. So in motor generator, so yesterday class we have already discussed about it, the regenerative braking. Suddenly that one of the source is when supply is omitted, then what happened? Then from power will come from load side to source side directly for that instant. So for that instant you can say like that it is regeneration. But practical knowledge, when you are going to be tested in practically, so in that case you can say like that you have to include one driving motor. Okay, to pilot motor, one driving motor to drive the test motor. Okay, so what is that study? So the motor acts as a generator and developed and the induced voltage Eg. The Eg must be greater than the supply voltage Va. The armature current is negative but the field current is positive. Okay. The kinetic energy of the motor required to the supply, a series motor usually connected in the self-excited generator. So that you can understand. Last class one question has come. So this is for series motor. So you know that configuration has changed. So I am telling you the special configuration. So you have to reversing. The changeover switch is there. The changeover switch is there for reversing the field. Otherwise, you know the demagnetizing effect. So if directly it is in different way, current direction in field is different, so it may cause for demagnetization or the or the damage of your main field. Okay, series motor field. So that's why before doing the regeneration braking, so both of the things should be synchronized, going of the regeneration braking and the changing of the switch. Okay, for that field both should be done in simultaneously. Okay, that you can observe here. Okay, so it is your Ia equal to If and you can see the regenerations. Okay, so motor is there and it is your RF, LF both are there. Okay, it is your VF. So it is for separately excited motor. Okay, and this is for the series motor. By changing the terminal, reversing the, so what is happened for the self excitation, the necessary of the field current aids the residual flux. This is normally accomplished by reversing the armature terminals or the field terminals. Okay. So for the operating mode mean dynamic braking. So in case of dynamic braking, what you need to do? So for the dynamic braking, you can understand that the arrangement is shown in the figure are the similar to those of the regenerative braking, except the supply voltage. So VA is replaced by the braking resistance RB. Okay, so it is your RB means braking resistance. So supply is removed. Okay, supply is removed with the RB. So as per your idea, you can say like that in regeneration braking, what happened? So output voltage. Okay, output voltage means load side to source side. It is coming. Okay, but second stage of that regenerate braking. So in coasting period, normally we are doing the regenerative braking coasting period. After that, we can switch from regenerations, okay, from coasting period to braking period, my deceleration period. So what we are doing, so then after certain time for the after doing the regeneration, then we just connect, okay, some of the parallel resistance that will also be there, so directly to the armature of the motor. So additional energy will be dissipated through that RB, okay, means it is dynamic braking resistance, okay, that is a braking resistance RB, okay. So kinetic energy of the motor will be dissipated through the RB, so that may cause for additional energy losses, okay, so that may cause for additional energy losses. So so that may cause for your additional energy losses. So that's why we have to the normal EMU means our city ride. So we are using the dynamic braking concept. So a lot of energy will be wasted over there. But mainline service, we having some capability to reverse back some of the additional energy to the mainline. Means overhead track of the overhead line of the mainline track. So in that case we can follow that regeneration, then dynamic braking. But in local, when city ride, directly we should go for the dynamic braking. So the plugging operations also be there, okay. So in plugging operations, what happened, plugging is type of a braking, okay. In this type of braking, the connections for the plugging are shown in the figure, okay. The armature terminals are reverse, okay. Armature terminals are reverse, okay, while running condition. The supply voltage VA and the induced voltage EG act as the same direction, okay. So plugging means it is again one type of reverse braking, reverse motoring, okay. So means it's the braking conditions, okay. The armature current is reverse, thereby the producing the braking torque, and field current is positive, okay. For the series motor, either the armature terminals or the field terminals should be reversed, but not to the both, okay. So that's the conditions, okay. So here you can see that EG, the terminal you have changed, that's why it is coming minus then plus, again the same thing, minus then plus, okay. So it is your motoring condition, okay. So same thing is there, so it is LF RF means both are there, okay. It is your RA, okay. So it is your RA, so all the things are there in the plugging conditions, okay. So what are the most important operating mode, okay. So first we are changing first we need to identify the polarities of the supply voltage, back EMF and the armature current, okay, for the separately excited motor. So that we need to study first, okay. So what we can see that forward motoring means quadrant on, okay. So forward motoring, it is called the quadrant on. So VA, EG and IA are all positive. For quadrant on, everything is positive. So torque and speed both are positive, so power also means positive. Then forward braking, okay. So forward braking means quadrant 2, okay. So forward braking means quadrant 2. So the motor runs in the forward directions and induced EMF EG continues to be the positive, okay. So EG is positive, for the torque is negative, and the direction of energy flow is definitely reverse. The armature current must be negative. The supply voltage V should kept in the less than the EG, okay. That means regenerative braking, okay. Then reverse motoring, that means it is known as the quadrant 3. So VA, EG and IA all are negative, okay. The torque and speed are also negative. So in this quadrant, to keep the torque negative and energy flow from the source to motor, the back EMF EG must satisfy the conditions VA greater than EG. The polarity of EG can be reversed by changing the directions of field current or by reversing the armature terminals, okay. Okay. During the reverse braking, the quadrant 4, the motor runs in the reverse direction. VA and EG continue the negative for the torque to be positive and the energy to flow from motor to source. The armature current must be positive. The induced EMF EG must be satisfied the condition. So mod V less than EG. So that portions in reverse motoring and reverse braking. So reverse motoring VA armature voltage, armature voltage must be greater than your generated EMF. But here the reversing is happening for reverse braking. So armature voltage, mod of armature voltage less than your EG. Okay. So that must be satisfy the conditions. So four conditions are there. Okay, for the four quadrant operation. So it is your four quadrant operation. Okay, so I think all of you are able to understand. So in four quadrant operations, you know that that I am telling you. So it is your forward motoring, the configurations VA greater than EG. Okay, then reverse braking. So it is your VA less than EG, means regenerative braking. Again, mod A greater than EG, mod EG. Okay, so both are negative. Okay, so it is called reverse motoring. So reverse motoring, but reverse motoring also motoring mode. Okay, so you know that EG, how do possible? So you are changing the terminal of VG and VA and EG. Okay, so next step in reverse braking, what you need to do? So you are doing the plugging. So mod of VA less than mod of EG. Okay, so it is your torque and speed. So torque speed characteristics given below. So here power is positive, torque is positive, speed is positive. Here power is negative. Basically torque is negative. Okay, minus x-axis. Speed is positive. Here torque and speed both are negative. So power is positive. Here speed is negative but torque is positive. So again power is negative. Okay, so first and third quadrant power is positive. Second and fourth quadrant power is negative. And that's why it is called the forward braking, and it is known as reverse braking or the plugging. And it is forward motoring, but it is known as reverse motoring. As the VA and EG both are reverse, so the outcome also the same with your first quadrant operations. Okay, so again it's a continuation of the four quadrant operation. Okay, so here you can see the single phase drives with your power electronics converter. So first you can use the single phase AC supply. Okay, that is your single phase AC supply. It's control mode. Okay, so here you are using that phase control converter, means you know the silicon control rectifier means SCR. So that we can also use to study the operations both the cases. So it is your single phase AC supply, and you know that is your control rectifier. Okay, so control rectifier, so you know that it is your mutual inductance LA and LM and LA. So RA is there and motoring operation. So you can change the firing angle of this SCR. So you can vary the terminal voltage of the motor as well as the terminal voltage of the field. If the armature circuit of the DC motor is connected to the output to the single phase control rectifier, the armature voltage can be varied by varying the delay angle of the converter, that you can change the alpha A. Alpha A means how would you change that value of alpha A? So you can consider like that manner. So firing angle is your alpha. Okay. So how to select that value of alpha, how to change it practically? Just try to understand, try to realize the problem. Okay, so if you have one circuit, okay, so rectifier is there. Okay, so first cycle, you just consider the first cycle. So first cycle means how much time period. So for 50 Hz cycle it is 20 millisecond. For 50 Hz cycle it is 20 millisecond. For the rectifier sorry. So for the rectifier cycle means, so first half cycle it is 100 Hz means 10 millisecond. So 10 milliseconds shows you 180 degree. Okay. So 10 milliseconds shows you the 180 degree means entire cycle. Okay, not entire cycle, first cycle. So it is 180 degree. So for entire cycle it will be 360 degree. But we are considering the half cycle. Okay. So 10 millisecond equal to 180 second. Okay. So 1 millisecond equal to what? So 18 degree. Okay, so by that way you can select, you can prepare a truth table. Okay, if you are able to prepare a truth table, then you can easily control it to the microcontroller based control. So how much control you want to get? Okay, so 1 millisecond it is 18 degrees, so 0.5 milliseconds, so it is coming 9 degree. Okay, so now if you change for means multiplications of the 9 degree. Okay, so it is possible. So 1 millisecond. So you can change it in different manner. So 1 degree you can consist like that way. So 180 degree means 100 milliseconds. Okay, so 1 degree equals to 100 millisecond divided by 1 degree. So if you are changing for the 4 degrees, so it will be multiplied, means 4 into 180, 4 into 100 millisecond means 100 into 10 to the power minus 3 whole divided by 180 into 4. So that's the multiplication, means that much amount millisecond you can represent, or the 10 to the power minus 3 you can say like that is millisecond range. Okay, so 100 by 180, so it is coming 10 by 18 into 4 into 1 into 3, like that way you can change 1 degree deviations, and it can define the in the millisecond range. So that's why you can control, you can able to control the firing pulse, and every changing of the degree you can able to get the what is the what voltage is coming. Okay, what is the value of VA. Okay, what is the value of VA, that means that voltage is appeared across the motor. Okay, so another thing is that LM is called that smoothing inductor that I told you in my last class. So normally smoothing reactor means, so you will get some pulse DC na? So it is the pulse DC. So if you pass that DC through the smoothing reactor, so you will get the constant value of DC. Okay, that you can observe in the just in the locomotive or the EMU also. Okay, so that smoothing reactor is there, one box is there named as a smoothing reactor. Okay, so that provide you the fixed DC value. Okay, more or less fixed DC value to the motor. Okay, so converter also applied to the field the control of the field current by varying the delay angle. Okay, by the varying the delay angle of alpha F. So alpha F for your field and alpha A for your armature. So basic circuit element, single phase current converter for separately excited motor is shown in the figure. So low delay angle armature current may be discontinuous. So delay angle or the firing angle, okay, both are same. So that low delay angle means the options more of the you will get most of the voltage, but if the firing angle more, so it may be chances of the discontinuous mode of operations, means your armature current, okay, may be touched to the zero value. So it is, in that case it is known as discontinuous mode. Okay, so you should keep remember. So sometimes you should not go for the discontinuous mode of operation. Okay. So what are the important things for the single phase drives? Okay, so important portions means that depending on the type of the single phase converter, so what are the types you are using of the converter. Okay, so single phase drives maybe subdivided, single phase drives may be subdivided into 4 things. Single phase half wave converter. Okay, half wave converter means you are considering only for half cycle, means only one cycle. Okay, it is having 2 cycle na? So for AC, so you are considering for the half cycle. Then single phase semi converter. Semi converter means this is that machines is an example of a RLE load. Okay, so semi converter is responsible for freewheeling. It will be responsible for working as a freewheeling diode. Okay, so sometimes that inductor is there, so due to that value, so sometimes there is a required for that freewheeling diode. Okay, for making that current zero. Okay, so that's the reason for using the semi converter. Also the cost cutting. Okay, single phase full wave drives. Okay, single phase full wave drive means you can control both of the cycle. And finally the dual converter. Dual converter means, so single phase dual converter means both of the breaking, all those case half wave, semi converter, full converter, also the only if you are using the control switch without having any anti-parallel diode, so the breaking is not able to possible for single phase full wave converters also. That's why we should go for the dual converter. Okay, single phase full wave dual converter. So in this case braking as well as motoring, both the conditions may be possible. Okay, you can see the circuit diagrams for different here you can see the first quadrant operations. Okay, first quadrant operation means VA and IA both are positive, so it is half wave converter. Okay, only one SCR is there, so it will work for the only one half cycle, so there is no anti-parallel SCR with that one, so that means only it can carry for the first half. When that anode and cathode both are there, na, so if it is PN junction in the forward bias only it can work. So what we need to see that single phase half wave converter feeds a DC motor. Okay, as shown in the below, the armature current is normally discontinuous unless a very large inductor is connected in the armature circuit. Okay, so that's why one additional resistance is required, but you know that additional diode is there for the freewheeling purpose. Okay, for the freewheeling purpose additional diode you need to install both of the cases. Okay, so you are using the full wave converter. Okay, still it is symmetrical. Okay, symmetrical semi converter. Okay, if it is asymmetrical, when it will be possible? So exchanging. Okay, so exchanging means one leg, if the diode is changing that positions, okay, so that diode is there. Okay, you are just cross changing, means you just put this diode in this leg and the SCR will be there, so it will be asymmetrical. In that case no freewheeling diode is required for the across of the field. Okay, so freewheeling diode is always required for the DC motor load and it is one quadrant drive. Okay, so that applications of the DC drives are limit maximum 0.5 kilowatt power level. Okay, so you know the circuit diagram, sorry, you know the characteristics that IA is there, IA equal to just fixed sub voltage. So then alpha value you are giving, so up to pi, that I am telling you 180 degree maximum. Okay, it can vary 0 to 180 degree, so you are changing the firing pulse. Okay, so alpha is the firing pulse. Before that it will not there, it will not work, so there will be no voltage, no current, armature current. If there is no voltage, so no current will be there, so that's why you will not get that value. So IA will be coming here. Okay, so that portion after giving the gate pulse. Okay, then before the working condition, then what will be that IA will be there, so up to that much it is not there, then after that again you can observe. So it is there single quadrant operations of your induction, sorry, of your half with your half wave converter. Okay, if you have a converter, and half wave converter is the field, in the field would increase the magnetic loss of the motor due to the high ripple content of the field excitations current. Okay, so why it is called ripple current, why it is ripple? So you can see the structure is look like a square wave. Okay, so what will be the problem? So normally square wave means if you go for that Fourier analysis, so fundamental one is normally sinusoidal. So we are considering for the fixed for the 50 Hz system, so 50 Hz is the fundamental one. So square wave means inherently there is a generation of the harmonics, but what happened in the case of motor, already some of the inductor, if you see that coiling is there, so that can take care about your filtering effect. So in this case additional filter is not required, but that filter means that inductor means windings are there, armature winding and the field winding, that can take place the working of the filter. So both of the options, both of the working will be there. So you can see the first quadrant operation. Then full wave converter drives. Okay, in case of full wave converter, what happened? So bridge, full wave, both of the cycle it can be operated. Okay, so braking as well as motoring, both of the options may be observed. But in this case, what happened? One diode is required. Okay, so that diode is not mentioned here, but that diode is important. Okay, so if you know that V by I think that equation 2 Vm by M cos alpha. Okay, the expression of the full wave converter output voltage expression is maybe 2 Vm by pi cos alpha maybe. Okay, so so that means you know that maximum voltage more or less up to 2 times. Okay, maximum voltage up to 2 times. So in this case the stress, the switches, when you are selecting the switches, so that voltage stress will be more. There is chances to change the to maximum limit of the voltage. That's why you know that current also changing. Okay, so plus I to minus I, so twice rating of that current also will required. So I A minus of minus IA. So it is look like a 2 IA. So twice of your armature current. So it is a change to the maximum level up to twice of your current. Okay, so that type of thing you have to be keep in your mind when you are doing that observation. So armature voltage, armature gonna gives plus VA or minus VA, the following operations for the first and fourth quadrant. So that means when you are changing that terminal, so plus VA to minus VA, so how much voltage stress will be observed across your switches? So that is VA minus of minus VA, okay, or minus VA minus a plus VA. So minus 2 VA and plus 2 VA. So the changing also possible. Plus 2 VA means the switch rating will be more than that armature voltage is there. So 2 times of your armature voltage. Okay. If it is not there, so there is a chances of the damaging of the switches. Okay. So for the 2 quadrant drives are shown in the figure and limited to the application up to 15 kilowatt. Up to 15 kilowatt you can see. Okay, so that drive we can operate. Okay, so it is your alpha 3. So firing pulse you have changing. So overall circuit it is working. Okay, so pi and 2 pi. So as per the changing of your firing pulse, it can work. Okay, so full wave converter, it is single phase full wave converter drives. Okay. So during the regeneration for the reversing of the direction of the power flow, the back EMF of the motor can be reversed and the reversing the field excitations. Okay, so that will be changed. Here you can see the single phase full wave converter drives. The converter, what they are suggesting, the converter in the field circuit could be full and even the dual converter. The reversal of the armature or the field allow the operations in the second and the third quadrant. Okay, the current waveform of the highly inductive load are shown in the figure below the powering action. So current descriptions are given here. Okay, so the converter in the field circuit would be the full and even the dual converter. It all are the in the full wave converter drives. Okay, the reversal of the armature of the field allow the operations of the second and the third quadrant. The current waveform is highly inductive, so show the figure. So I think we can stop today here. So but another I think we can stop here, means up to dual converter. Okay, single wave dual converter. Here you can see the structure of the dual converter, converter 1 and converter 2. In between them the machines, or you can say like the motor is connected. For the field, you know that another bridge circuit is there. Okay, so field terminal F1 and F2 is there. So input side one converter, okay, that is full control converter, but here it is in reverse directions. Okay, so alpha 1 plus alpha 2 equal to plus minus 180 degree. Okay, so the two single phase full wave converter are connected. Either converter 1 operates to supply the positive armature voltage, okay, that is VA, or converter 2 is operated to supply the negative armature voltage or minus VA. Converter 1 provides the operations in the first and the fourth quadrant. Okay, so both are in motoring. One is motoring, another one is reverse motoring. Okay, and reverse braking. Okay, and the converter 2, it operates. So converter 1 operates the first and fourth quadrant. So converter 2 will operate in second and third quadrant. Okay, it is the fourth quadrant drives the permits the 4 modes of operation: forward powering, forward braking, or the regenerations, or the reverse powering and the reverse braking. Again the regeneration in reverse direction means motoring. It is limited applications up to 15 kilowatt. The field converter could be the full wave or the dual converter. Okay, so I think all of you are able to understand up to the operations of the dual converter. So today I am saying stop my session here. So today I just, then in my next class I will discuss about the 3-phase. Okay, so I discuss about the 3-phase drives. Okay, so what is the advantages over the 3-phase drives over the single phase drive. Okay, so so if you have any doubt, you please note it down. So in my next class I can discuss about your doubt. Okay, so thank you.